Hey, this is Mrs. Weethy and I'm back for Unit 6 video lesson number 12 on ideal gases. How can you calculate the amount of a contained gas when the pressure, volume, and temperature are specified? Because in the previous combined gas law, we really only looked at the pressure, volume, temperature, and the amount was always constant. But you can have conditions in which you can change the amount of a gas. So that's what we're going to focus on. The number of moles of gas is directly proportional to the number of particles. Moles must be directly proportional then to the volume. So if you increase the number of particles, you're increasing the number of moles, and therefore you have to increase the volume. You need more space when you have more particles if you're not in a sealed container. And so that's what we're looking at. We're not looking at having a constant volume. Our volume can be constantly changing. So if you take the pressure and the volume and you divide that by the temperature and the number of moles, that is going to be equal to a constant. So how do we get that? Well, we can introduce moles into the combined gas law by dividing each side of the equation by n. So let's see that. So we have P1 times V1 over T1 is equal to P2 times V2 over T2. So we're going to introduce the number of moles. We're going to divide each side by the number of moles. So we have N1 on the left side and N2 on the right side. And so when we have that equation, if you have all of your variables set to a constant condition, let's say all those conditions we have at STP, then that will equal a constant. So again, let's take a look at that a little bit further. This constant holds true for the ideal gases, and those are the gases that conform to the ideal or to the gas laws. So if you know the values of P, V, T, and N, the pressure, the volume, the temperature, and the moles for one set of conditions, then we can calculate a value for the ideal gas law constant. And that is equal to the symbol R. So when you see the symbol R, that's the ideal gas law constant. And that is equal to PV over Tn. Pressure times the volume divided by the temperature times the number of moles. So at STP, at standard temperature and pressure, at standard conditions, we have 1 mole of a gas occupies 22.4 liters at STP, and this is called the standard molar volume. Otherwise, we can set this up as a conversion factor. 22.4 liters over 1 mole is all gases at STP. 1 mole of any gas is going to occupy 22.4 liters. Avogadro actually found that relationship. STP is standard temperature and pressure. We talked about that before, which is negative 273 Kelvin and 101.3 kPa. If we use these conditions at STP, then we can calculate the ideal gas law constant just by plugging it into the equation. So we have, and this isn't negative 273, it's just 273 Kelvin. So we plug in the pressure at STP times the volume at STP, divide that by the temperature at STP times 1 mole, and the value is 8.31, now look at the unit, liter kPa over Kelvin times mole. Now this gas law constant can change with different pressure units. Notice the pressure unit here is kPa, but at standard pressure you can have 760 torr, you can have 1 atmosphere, so therefore that gas law constant can change with the unit. Let's take a look at that. The common ideal gas law constants, 62.4 liter millimeter mercury. Now look, that is the pressure unit, millimeter mercury over mole Kelvin. Okay, or you can have 8.314 liter kPa over mole Kelvin. So the difference is in the pressure unit. So when you're doing ideal gas law problems, you have to make sure that you choose the correct gas law constant, the one that has the pressure unit that is in your problem. Okay, so the gas law, the ideal gas law, includes all 4 of the measurable variables: the pressure, the volume, the temperature, and the number of moles. And this is the equation: PV equals nRT. So that's the ideal, or the combined gas law, and now the ideal gas law. Those are the 2 gas law equations that you need to learn. So, problem time. At 34 degrees Celsius, the pressure inside a nitrogen-filled tennis ball with a volume of 0.148 liters is 212 kPa. How many moles of nitrogen gas are in the tennis ball? Okay, so our givens, list them. We have the pressure, we have the volume, and we have the temperature, 34 degrees Celsius. And although we're not given the ideal gas law constant, because our pressure is in kPa, we know that we need to use the ideal gas law constant that has the pressure unit in kPa. Now, another thing that we have is the temperature in degrees Celsius. So we have to change that to Kelvin by adding 273, which is 307 Kelvin. Make sure you remember to do this step. Our unknown is the number of moles, and our equation, PV equals nRT. Now what we can do, we can solve this equation for N, for the number of moles. And how do we do that? We can divide both sides by RT, and that gives us the number of moles is equal to the pressure times the volume divided by the constant times the temperature. Plug in our numbers, divide out the units. So we see kPa's divide out, liters divides out, and Kelvin divides out. That's going to leave us with the number of moles. Do your math, and the number of moles is equal to 0.0123 moles of nitrogen. So that since the tennis ball is filled with nitrogen. Okay, so under what conditions does a real gas differ from an ideal gas? Because we've been looking at ideal gas law conditions. An ideal gas is one that follows the gas laws at all conditions of pressure and temperature. Particles have no volume. There are no attractions between particles and the gas. Basically, it is the perfect gas, but there's no gas that conforms to any of these assumptions. So at many conditions of temperature and pressure, real gas behaves a lot like an ideal gas, but the difference is a real gas does have volume. There are attractions between the particles. There's the London dispersion forces between the particles, and because of these attractions, the gas can condense or even solidify if we undergo sublimation when it's compressed or cooled. Real gases differ most from an ideal gas at very low temperatures and pressures. So those are the conditions in which real gases are different from ideal gases. And this is just a little graphic to show you the different conditions. So the straight line right here is ideal gas. So this is the conditions you would expect, but we see at different temperatures and pressures, these real gases deviate from that ideal behavior. And so this then is the end of video lesson number 12. And like always, I'm going to leave you with a be happy and have fun, but no dancing today. This is Mrs. Wheathy, so long for now.